Bam, bam, bam. Bam, bum, 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 bum.
Bet you never thought you'd see a video like this on my channel. I want to go over what I'm doing a little and sort of explain things before I get too deep into it on my machine. This video is meant to sort of compare and contrast the various methods of auto bed leveling that are available for 3D printers in general. Here, I'm basing it on the leveling system of the Elegoo Neptune 3, but there are other 3D printers on the market that use this similar resistive strain gauge system, such as the Creality CR6. The methods I'll be covering are some of the more popular systems available on the market, such as the resistive strain gauge, which is the stock system on the Elegoo Neptune 3, the inductive proximity sensor, capacitive proximity sensor, and a probing sensor. In my case, I'm going to be using a BLTouch, but there are other various probing systems available, such as the Creality CR-Touch, and various knockoffs you can find on Slamazon and AliExpress, like the G-Tech 3D Touch. As a side note, I've come to the conclusion that G-Tech is sort of like the honey badger in a sense. G-Tech doesn't give a shit. G-Tech will just knock off whoever the hell they want. But I digress. There are some other solutions that I will not be testing, such as the simple Microswitch and various other proximity type sensors, but I'm covering the most popular of the bunch. The categories that I'm going to be covering are accuracy, repeatability, and speed of the system. And the reason for that is things can be accurate, but not repeatable. For example, I'm really good at telling time about 85% of the time, but that other 15% I'm usually off by about an hour or so. Usually I'm within an accuracy of about 6 minutes, but my repeatability isn't quite that good. And another reason why I'm doing this is because the faster you can do bed leveling, the better, because let's face it, people in general are impatient, and to have a system that takes 7 minutes as a baseline, even on a 2-hour part, is not really the best. So for the start of the test, we're going to get into the resistive strain gauge, and there are some pros and cons to each of these systems, and I'm going to go over them as we go along. The resistive strain gauge is the standard system that comes on the Elegoo Neptune 3, and again, it comes on the Creality CR6. It's basically a little wafer that gets glued onto this metal plate, and the metal plate has a little bit of flex to it, and as the plate flexes, it sends a resistive signal to a receiver box, and the receiver box then takes that resistive signal, which is an analog type signal, and turns it into a binary output, such as an on and off switch. That on and off signal is then sent to the motherboard, and then the response from the motherboard is to signify whether it is on or off. The pros to the standard strain gauge on the Elegoo Neptune 3 is that there's no firmware changes because it's a stock system. It comes set up from the factory. It is accurate and it's repeatable. There's no special Z offsets that need to be taken into consideration. You run the auto bed level on the DWin touchscreen. The nozzle will come down to the bed and you can check it with a piece of paper. When you're running the G29 auto bed level, it doesn't do this additional step. It just goes based on the Z offset that you have set up in your EEPROM. Another good thing about it is that it can measure the entire table because it's essentially the nozzle, and the nozzle can get everywhere onto the build surface. The con to the resistive strain gauge is that it can be slow, and if you try to speed it up, the readings are less and less accurate the faster you go. It's very finicky about cleanliness. You have to make sure that your nozzle is perfectly clean because if you have a little bit of goo on your tip, it will give you an erroneous reading. The metal plate can fatigue over time because there's physical contact that will move the plate, and there's physical contact that can tend to move the table, which then contributes to a less accurate reading. If you try to speed up your auto bed level or your auto gantry square, you can run into a situation where your Z travel is too fast and it will false trigger the sensor. Also, if you have an issue with binding filament, if your filament is binding up a little bit and there's a little bit of pull on the filament, it will then give an erroneous reading to the strain gauge. Another con to it is that it's harder to find replacement hot ends than it is a standard system. There is the Revo quick change hot end for the Voron that you can use, There are adapters available that you have to print out, but an off-the-shelf solution is not readily available at the moment. The next sensor we're going to get into is the inductive proximity sensor. There are 3 wires for the sensor. There is power, ground, and a signal wire. The sensors that I'll be using are NPN sensors, and that means that the signal wire is going to provide ground to a 24-volt potential. A PMP type sensor would provide 24-volt potential to a grounded circuit, so it's the opposite. Some pros of the inductive sensors are they are accurate and repeatable. They are non-contact, so therefore there is no fatigue in the system at all. They run at a higher operating voltage, which is less susceptible to interference than a 3.6 or 5-volt logic circuit. They're also available in different measuring distances. The one that I have on hand is a 4mm measuring distance. There are 2mm measuring distance, 4, 5, 6, 10, etc. A con of the system is that because it operates at a higher voltage, in my case I'm going to be using 24 volts off of the motherboard. There's a 24 volt supply coming off the motherboard. It requires an optocoupler to basically act as an isolated relay to take in a 24 volt signal on one side and then output the 3.6 logic voltage via the Z-axis limit switch I/O. If you watched my video previously about the strain gauge, you'll note that there is a 3.6 volt logic circuit. There's also a 5 volt feeder circuit that will power the resistive strain gauge I/O box. But in the case of the actual limit switch, we're going to be using the 3.6 volt and we're going to be using the ground to complete the circuit. Another con of the system is that it requires firmware changes. For example, we have to change the center distance and Z offset, but these can be changed in EEPROM. You don't have to change them in actual firmware. A major con of the inductive proximity sensor is that they only measure metal surfaces. And that means that they will only measure on a surface that is aluminum, steel, copper, etc. The next sensor we have is the capacitive proximity sensor. It's very similar to an inductive proximity sensor. They are accurate and repeatable. They are no contact. They operate at the higher voltage of 6 to 36 volts, which means that they are less susceptible to interference. The inductive proximity sensor, however, is available in a 5 volt variation. A capacitive sensor does not have a 5 volt version readily available. At the time of filming this video, I have yet to find one that operates on 5 volts, at least reliably. They're also available in different measuring distances, but there are versions that have an adjustable potentiometer on the back of the sensor, which allows you to dial in the distance of measurement. The one that I have is actually a G-Tech unit, and it does have the adjustment pot on the back, as well as the LED light to signify that it's being triggered. These offer the same or similar cons of the inductive sensor. They require an optocoupler, which requires more knowledge of industrial electronics because you have to wire in the optocoupler. They do require the firmware change for the center distance and Z offset and some various other little settings. And another thing is that these sensors can trigger on pretty much any surface. So you can trigger these on a G10 bed, you can trigger these on a glass bed, you can trigger these on the PEI sheets. But if you have anything on your bed and it falls in the range of the sensor, it will false trigger on that item. Not that you should have anything on your bed surface while you're printing, but stranger things have been known to happen. The next system that I'll be using is the BLTouch probing sensor. Again, there are other variations such as the Creality CR10 and the G-Tech, or whoever else wants to claim it as theirs. I believe Big Tree Tech offers a 3D touch, and other outfits also offer the same basically knockoff BLTouch. The pros of this type of sensor is that they are accurate and repeatable. They are proven off-the-shelf technology. They are a plug-and-play solution as long as you have the necessary plugs for your solution to play. There are various wiring harnesses that are available off-shelf, and in most cases they offer a replaceable stylus tip. So if your stylus tip wears out, you can simply replace the tip. You don't have to replace the entire unit. Some of the cons to these is that they do require firmware changes, much like the other sensors, but they also require a PWM or servo signal, a 5-volt, and a ground. And these may not be available on the boards that you are working with. In the case of the Elegoo Neptune 3, there is a dedicated BLTouch socket on the board, but the Elegoo Neptune 3 Pro does not have the BLTouch socket, nor does it have any available PWM pins on the board to speak of. So you cannot put this type of sensor onto the Elegoo Neptune 3 Pro. Another type of sensor that I will not be covering is the simple Microswitch. Pro to these is that they are cheap. They're a couple of cents, really. They're under $1. They're decently accurate. They have both normally open and normally closed contacts on them, so you don't have to worry about ordering the right type of solution, and you don't have to worry about inverting pins if you order the wrong one inadvertently. So you don't have to change pins and firmware. You don't have to worry about ordering the right one. If you run into a condition where you're getting a false trigger, then you just flip from normally open to normally closed or vice versa. And as long as the logic circuit is set up for that type of switch, it'll still work. They're also easy to connect because they only connect to the Z limit switch input. You don't have to worry about additional wiring. The con to this switch is that they are a short throw, so therefore you have to put them onto an external mounting system, such as a clicky, which will pick up the Microswitch from a spot off of the bed to come down, touch, and then put it back, which requires additional logic in your firmware to do the retrieval and the replacement of the system. Compared to the other options in this video, they do tend to wear out quickly, and they're only decently accurate. They're not super precise. I would just like to take this time to thank Antclabs for sending me a BLTouch for this video. I reached out to them and they happily sent me one of their units to test out and review on this video, so thank you very much for that. Please keep in mind that this is an unbiased video, so I will not be giving any kind of special treatment to the BLTouch simply because the one that I have was free. When we're talking about connecting any of these switches to the Neptune 3, the Z-axis negative limit switch input is a JST XH 2.54 connection. It is one of these little white plugs here. It's a 3-pin white plug. A DuPont connector will work because the spacing is the same and the form factor of a DuPont connector is smaller, so it'll fit into here, but it won't lock into place. If you're using a BLTouch or a similar probing device, there is a BLTouch input section right here, which provides the servo, 5-volt, and ground. That is a DuPont 2.54 connector. And if you order your BLTouch from Antclabs, the part number for the cabling that you would need would be the SM-XD-1500, but an alternate solution would be the SM-DU-1500. The XD provides the 3-pin XH connector and also the 3-pin DuPont connector. If you're looking at the wiring on the BLTouch, the servo pin is yellow, the 5-volt pin is red, and the ground is black. So over here, if we look at this graphic, servo would be yellow, 5-volt would be red, and ground would be black. Do not get these backwards. You can burn something up. Both of these wiring harnesses seem to have the right pin out for the Z-negative limit switch. The 3.6 volt is on the outer pin. Looking at it in this orientation, it's the one on the very top. In order to do firmware modifications, or the easiest way to do firmware modifications is to use Visual Studio Code. And if you go to code.visualstudio.com/download, you can download Visual Studio Code for your operating system. Once you install it, you'll then go to the Extensions tab right here, do a search for Platform IO, and install the Platform IO IDE plugin. Once that's installed, search for Auto Build Marlin and install that. Restart Visual Studio Code, and when that's done, you'll have 2 extra icons on the left-hand side here. You'll have the Platform IO little bug head, and you'll have the Auto Build Marlin icon over here. To download the latest and greatest firmware, you go to github.com/narutofzr/neptune_3, and this is the official page for the Elegoo Neptune 3 firmware. You'll see at the time of filming that 4 days ago they released a 1.0.5 beta firmware for the ZMP Robin Nano V2.1. If you download the zip file to your computer and extract the files, you can then go to Visual Studio Code, go to the Platform.io bughead, select Open Project, find the folder that you extracted. In my case, I have it under Download/Neptune 3-Naruto Beta. The zip file that gets extracted has a very long file name, and therefore when you try to unzip it, it'll give you folder name too long errors. That's why I have it named Neptune_3-Naruto_beta. From there, we have to dig down into it to find the project file. So we'll click on this. We'll click on source code. We'll go into the ZMP Marlin-beta. And as long as you're opening a folder that has a platformio.ini file, it'll open right up in the Visual Studio Code IDE. If it opens up and you don't see anything on the left-hand side except for ZMP F401 Marlin beta, just click on it and it will expand the menu. To get to the files that we need, we have to click on Marlin. And then the two files that we would be digging into are the configuration.h and configuration_adv.h. If we click on configuration.h, you'll see here in this file, as I scroll down, there's a bunch of green information, and then there's a bunch of colored information. The colorful information is stuff that is currently being read in the program, and anything green is a comment. So a comment on a single line can be a double slash. A multi-line comment is a slash with a star, and then it terminates out with a star and a slash. My version of Marlin software has a lot of the modifications that Mike Lee put into his versions of software, which is the section machine portion. And these are switches that both he and I created for various options in the firmware. For example, if I comment out is dual Z, if you watch right here, you can see that this section right here goes dark. Anything with a hash in front of it is considered a preprocessor directive. So preprocessor directive runs before the compiler to check whether or not something is defined, and in this case with these conditionals, if it's enabled. And then further down the line, I've got some other types of preprocessor directives. There's hash if, there's hash else, there's hash elif, etc., etc. If I uncomment the hash define is dual Z, you can see again, these light up. This section right here is defining my E1 extruder section as my Z2 pin section for my second Z driver. If we do a search for has BLTouch, so we highlight has_BLTouch, Control F, and then we can search down, and you can see right here that there's 12 instances of has_BLTouch. So if we go down, we can see that if BLTouch is enabled, it will not invert the Z-min end stop pin, but if it's disabled, this section here will then light up, so the Z-min end stop inverting will then be true. Down here, same thing, the Z-min probe end stop inverting is false, and if we didn't have a BLTouch, the Z-min probe end stop inverting would be true. We're using the Z-min end stop input as the trigger signal. That's why there are two different hash defines for that. If I turn off the has BLTouch, it then will enable fixed mounted probe, and I'll show you that in a little bit, because if we're using a fixed mounted probe, we have different setting options than we would for has BLTouch. Another thing that we would have to change is our nozzle to probe offset value, and this is defined in X, Y, and Z values, so X, Y, and Z values. If has BLTouch is not enabled, then this would light up, and when this lights up, it's showing that the values inside of here are the original strain gauge values, and because they are essentially the nozzle to probe offset is going to be 0, 0 in X and Y, and 0.1 for Z because of the default 0.1 Z offset built into the Neptune 3. So when you run auto bed level, you'll see that initially it says Z offset in the hand controller of 0.1. There are also various other settings. Probe margin to stay inside an envelope within the table. X and Y feed rate for positioning of all your measurements. Probing feed rates for Z. If it has a BLTouch, it can be faster than it could be if it had a strain gauge. If you're using 2 or 3 or more hits for more accurate probing, you can also set a probe feed rate for your slow measurement. If you're not using a BLTouch, it will turn on this define probe tear, which will then open up this section here to try and limit environmental variables such as cables pulling on the carriage, or like I mentioned before, the resistance of the filament pulling on the strain gauge. It doesn't work very well, I'll tell you that. So you can see that just by enabling or disabling this section right here, this one little line, it then changes the way that the logic is handled for each of the solutions. I'll put a link to my GitHub page because I forked the Naruto firmware, but I also put my version of the configuration.h and configuration_adv.h so that when you download my version of firmware, these changes are already incorporated. Under the configuration_adv.h, these are the advanced options that you would have for a lot of different features that are available in the Marlin firmware. In this case, I have to check for enabled BLTouch, and then I can go through this BLTouch section, and you can see that there's 14 instances of BLTouch, but a lot of the stuff here is commented out. That's why it's green. So there's not really much that you have to worry about here, but it's always good to be familiar with some of the stuff inside of this file. For example, I use G34 auto gantry squaring, and right now my table isn't quite exactly where it needs to be. I have to kind of adjust it a little bit. So I increase the number of Z-stepper align iterations from 5 to 10 so that when I'm running the gantry squaring, I have 10 tries to get it right. After 4 or 5 iterations, it typically falls in to the alignment that I have set here, which is the 0.02. But there are times where it's a little bit heavy and I want to go 2 or 3 more times just to make sure that it's right. So if you go to the Teaching Tech YouTube channel, he's got a lot of useful information on modifying Marlin firmware. So I'm not going to get too deep into it. But once you're done making your changes to your configuration files, all you really have to do at that point is go to Auto Build Marlin, click on Show ABM Panel. If you have a previously compiled version, just click on Clean. And then once you hit Clean, the clean icon will go away. This link right here will disappear. And just click on Build. And when you click on Build, it'll compile the file for you. If there are any error messages, they'll come up down here. And when the software is finished being compiled, it will automatically open up the file location and select the file for you. So then you just copy that file onto your SD card, power off your machine, plug the SD card into the slot, power it up, and it will flash the firmware for you automatically. And then from there, you can remove the SD card and hopefully everything will run fine. So without further ado, let's get over to the machine and we can start our test. Leave it to me to try to clean up my SD card and delete all the footage that I had. So to get started, you can see I made a new linear truck adapter for the X-axis. I added this little bracket onto the side here. It's got hole patterns in it to hold both the BLTouch and the M12 threaded capacitive and inductive sensors. I've got the strain gauge set up in the firmware to take measurements. First measurement I'm going to do is I'm going to do the M48 repeatability test. It's going to give me 10 hits at fast rate and then 10 hits at slow rate. Well, it'll do fast, slow, fast, slow. It'll give me 10 hits and it'll give me the standard deviation of each of those hits. And I'm going to record those into a spreadsheet. Once I do that, I'm going to increase the speed, and we're going to run it again and see what the resulting measurements are with the increase in speed. I'll keep doing that until I see a large variation or a large measuring window that just doesn't seem to be all it's cracked up to be. Okay, so I ran the M48 test 10 times. I documented all of the results right here using M48 at 25 millimeters per minute. You can see that we have a minimum, a maximum, and then the range. We have averages for each of them. Our average negative range is 0.0297 millimeter, and our average maximum range is 0.0369 millimeter. Altogether, we have an average min-max range of 0.0666. So from the mean of 0, it fluctuates in both the positive and negative direction as far as where the sensor actually picks up, which gives us an average, after the 10 tests, gives us an average standard deviation of 0.022891. So I'm going to now run it at 50 millimeters a minute, and we're going to document the change there. I don't know if it's going to go any higher than that, because I know that the initial bump, you can actually see the strain gauge move, and you want it to move a little bit to record the value, but you don't want it to move so much that it actually twists the nozzle. So I think we're going to pretty much cap out at the 50 millimeters a minute. I'd be interested in seeing how fast I can go with the rest of these systems, though. So the first thing I'll do here, I'll clean my firmware. I'm going to go into my configuration.h. I'll come down to my slow feed rate. I'll change that from divided by 4 to divided by 2, because remember, we're taking this value here, 100 millimeters per minute. We're dividing it by 2, and we're going to get our slow feed rate. Okay, so I ran through the 10 iterations with the strain gauge set to 50 millimeters per minute on the fine feed. And you can see here, the negative average didn't change very much, but the overall is all over the board. It goes from minus 0.045 to positive 0.008. It's not very reliable. It's not very repeatable. The maximum number average is a positive 0.075. The range is 0.104. So compared to the 25 millimeter per minute feed, you can see that it's almost double. The faster you go, the more this is going to get progressively worse. Even our standard deviations, the average of the standard deviations is basically almost double. So that just leads me to believe that I can't go any faster than this 25 millimeters per minute, or else it's just going to get so bad that you won't even be able to use the system. So I'm going to recompile the firmware and continue on with my testing. My next test for the strain gauge is going to be auto bed level. So I'm going to keep running through auto bed level and see what each of the measurement points come out to be. I'll do that without auto gantry squaring. I'll run the ABL test 10 times as well. And I'm going to do this with all of the sensors, and I'll be able to kind of get a ballpark of what each of the points measure out to be as an average, and that will help me calculate the standard deviation as well. Okay, so I ran through 10 iterations of auto bed level with the 2-point hits. I've got a total time of 2 minutes and 55 seconds in its current state, and I took all those values out of Octoprint. I copied them, pasted those into here directly, which then creates a comma-separated field like you see here, breaks them into rows and columns. So you can see that the values, they do vary. Minus 0.3, minus 0.33, minus 0.257, 262. I took all those values, I averaged each of the points in this area here. Then I did a standard deviation of all those 10 points. Each point got its own standard deviation. And then I did an average of the standard deviation values, which gave me these numbers here. But let's see if we can do better. I'm going to hook up the capacitive sensor, then the inductive sensor, and then the BLTouch, and we will do the same tests on all of those, and we'll see what the numbers look like when we are finished.
Don't try this at home, kids.
So I've got 24 volts coming off of the motherboard, 24 volt positive going to this rail on this breadboard, 24 volt negative, or 0 volt common if you want to call it that, coming to the negative on this side here, which makes this entire rail positive, this entire rail negative. From there, I'm tapping in to negative voltage, positive voltage, and signal, and that gets sent to these wires here on this capacitive sensor. The blue wire is my ground, the brown wire is my positive, and the black wire is my signal. This is an NPN sensor, so the signal wire supplies ground. Over here, I have that attached to this optocoupler. I've got 24 volt positive going to the input side, the right side of the optocoupler, and then I've got the ground being served via the signal. So the signal triggers the ground, which completes the circuit here, which then ties into the output and the ground on this side here, which is then feeding into the center wire, and if this were plugged in, the right wire, which are the Z negative limit switch and the 0 volt ground or common collector. If I do a Z home, you'll see that when it comes down, the nozzle doesn't touch, but it does sense it from the capacitive sensor. If I trigger the sensor with my finger, you'll see that it lights up. Not only does that light up, but also the optocoupler lights up to let me know that it's being triggered. I have to set the X and Y offset, so I'll just do that in firmware so that I can use it for both this capacitive sensor and this inductive sensor. So I've got the BLTouch plugged in, powered up, but it's not serving any purpose at the moment. But the inductive sensor, keep this in mind. An inductive sensor will only sense metallic objects. So you can see it's tied in, it's hooked up, it's working. I actually have it tied in directly with the blue, black, and brown. The capacitive sensor I kind of had to rig with a bunch of Arduino leads because they didn't send me a long enough cable. But the inductive sensor's hooked up, but it'll only sense, you can see right here, it'll only sense metal. That's the downside to the Neptune 3 Pro, is that it's using an inductive sensor, which would mean bye-bye G10 sheet. Now G10 sheet, if I put this underneath here, because I'm reading capacitive signal, or capacitance if you will, if I just take this and lift it into contact or get it close to contact, you can see that it triggers. There is an adjustment pot on top of the capacitive sensor that allows me to fine-tune the travel distance in which it senses. I've also got some adjustment built into my bracket. Yeah, I'm cranking this one up. So here's the results of the first measurement. Yeah, I'm going to YOLO this thing. This is too good. So I'm going to be honest with you guys. When I first started running the test with the capacitive sensor, I was running it with the 2 hits, and I was getting good results. But then I decided to remove the multiple probing, and I found that the Z probe feed rate slow, when I took these values, or this value, and I put 100 divided by 4 up here, the probe hits were ridiculously slow. So I don't know if there's some kind of hoodoo voodoo going on in the background with this, or if it's not reading this on the second hit and it's still just defaulting to the 100. I don't know. But that being said, when I first was taking the measurements with the single point, I noticed that there was a little bit of a variation. I was getting from 0 to 0.015, 0.025 to 0.035. And I said, okay, well, these standard deviation numbers, they're exquisite. They are really good. So I bumped it up to 200 just to see. And again, standard deviation numbers, really good. So I bumped it up to 3. And again, standard deviation numbers from 100 to 300 barely changed. I went to 6. 6 then became 12. So I did testing at 600 and 1200 millimeters per minute, which even if these numbers were fudged, and this was 100 and this was 200, I'm still a few 100% faster with these values here. And if you look at the averages, I'm in better standing with the faster rates with the capacitive sensor than I was with the strain gauge. If we look at the standard deviation numbers and compare the strain gauge to the capacitive, I go down from 0.023, say, to 0.0058, and I'm that much faster. So I'm quite happy with the capacitive test results compared to the strain gauge. You can see down here I did the 16-point bed level test. This section here was with the 25 millimeter. This section here was with the 1200 millimeter. And the numbers, standard deviation numbers here for all of the 16 points being compared to one another in the grid pattern, I mean, these are pretty much spot on. As a comparison, I did the same thing at 600 millimeter, and the numbers didn't deviate all that much. So there's one thing that I do know for sure, and it's editing this video is going to be an utter catastrophe. So I've got the inductive probe in now, or the inductive sensor in now. I had to take one of the screws out to get the adjustment down where I needed it, but I've got it set. It's a 4 millimeter height sensor, as opposed to the capacitive that was adjustable. This one's a fixed length, but you can see that it does trigger. We're still using the breadboard and optocoupler setup running into here. I really didn't have to change anything, honestly, except for swap out the probe, because I had both of them plugged in parallel. So this is set up, ready to go. I ran the initial bed level, set the Z offset, and now I can run my repeatability test. So I can't help but get this maddening feeling that I'm missing something in this formula, because there is no way in hell that at 1200 millimeters per minute, I'm measuring at the rate that I think I am. Because if I figure out 1200 divided by 60, that's 20 millimeters per second. I've got the Z set to a travel speed of 20 millimeters per second in Octoprint, and the upward and downward motion of moving the machine manually is by far quicker than the probing movements. So my thought is that it's using the accurate measurement value based on this divided by 4, but somehow translating it in a way that by putting 1200 divided by 4 here, it doesn't quite, I don't know. There's something going on here that I haven't quite figured out. So that being said, I'm going to go based on the assumption that I was originally correct in my thought process, that we're at 25 and 50, and then here we're going to say we're at 150 and 300. It just makes more sense to me, because there's no way that this is going to give me the feed rates that I'm seeing in the measurements. Just safe to say that we went from 100 here to 1200 here, and whatever it is what we're seeing here reflected in our spreadsheet. So now I've got the higher feed measurements. You can see that on paper, the min and max values of the inductive sensor are way, way, way tight. They're like super good. I think they're almost too good, because I cranked up the Z travel speed even further and did an M48 for the repeatability test, and it gave me straight zeros across the board. It's impossible. There's no way that it's sensing that quickly, that accurately. So there's got to be something messed up with the delay time or something with the measurements. That being said, down here, this is a little bit more realistic, because the numbers of the bed leveling seem to match up pretty well with the numbers that I was getting with the capacitive sensor, and the standard deviations are very close to one another. So that, to me, is a little bit more real world than just having it hopscotch in 10 places and give me a result that was not quite what I thought or expected it to be. I don't know. There's something up with that. So now it's the moment everybody's been waiting for, the BLTouch. Let me install that real quick. Change firmware to accept it. I'm going to start off with a baseline of 600 because that's the value I had here. So I forgot to get the gratuitous money shot of the BLTouch. So it's in place. The firmware has been flashed. Obviously, I'm taking some measurements on it right now. And let's see how our tried and true Antclabs BLTouch holds up to its contemporaries. You know, I'm really losing my mind because it took me until I was editing down to realize that I inadvertently crossed the colors of my capacitive and inductive fields. I wanted to keep a colors matching theme going on the top here, capacitive being the green tip, inductive being yellow, the BLTouch having the red LED, and then the nozzle being that brassy color. But I kind of deviated a little bit. So I did all of my testing, my 10 points with the M48 and my 10 auto bed level cycles. And the numbers that I came up with are pretty interesting. You'll see that at the top here, my mins, my maxes, my range numbers. If you compare the data from the strain gauge to all of the other sensors, you'll see that the capacitive is kind of the second least accurate, and the inductive and the BLTouch are kind of neck and neck in a lot of the scenarios. There does seem to be a little bit of a difference in standard deviation as you get faster with the feed rate, but we're splitting atoms at this point here. If we get down into where the rubber meets the road, we've got our G29 results. Underneath that, we've got our average, and then underneath that, I put a field of the average range as it pertains to each of the hit points. And you can see that in the situation where it really matters most, all of the point averages based on the median values of these numbers here, the three options that I gave you are all really, really close to one another. And again, this is all in metric. So if you were to convert this to inch values for you Freedom Unit guys, these values are next to nothing. They're molecular level. Getting into the standard deviation values, you'll see that the standard deviations are pretty big on the strain gauge. And again, capacitive sensor, the inductive sensor, and the BLTouch are all very close to one another. And then I did an average of all the standard deviation values, and I came up with these average numbers here. So we've got 0.0386 for the strain gauge, 0.0081 or 0.0082 if you round up for the capacitive, 0.0073 for the inductive, and then a 0.00425 or 0.0043 for the BLTouch. So I can't say conclusively who the actual winner would be in this situation. It's more a matter of preference at this point. There would have to be a lot more real-world testing involved. Basically put, I would have to set up each sensor again, run a bed level check, and then do a test artifact every single time. And there's not enough time in a day to get all of that done in a timely fashion. So final thoughts. I don't think that there is any clear-cut winner. I do know that there is a specific loser, if you will, or at least preferred method. And the least preferred method is the resistive strain gauge. That thing can pretty much go by the wayside for all I care. I'm going to probably stick with the BLTouch only for the fact that it's still mounted to the machine, but also I don't have to do any fancy wiring for the BLTouch. It's a plug-and-play solution. But again, there is no clear-cut winner. The numbers were a little bit better in certain situations with the BLTouch, but otherwise, the inductive and capacitive sensors were also very accurate in their own right. The inductive being slightly better than the capacitive, but the capacitive having the capability of multi-surface probing. The BLTouch gives me all of that, plus it gives me an accuracy that rivals the other solutions. I think it's a fantastic little product, and I'm really happy that Antclabs was kind enough to supply one to me. But that's not to say that if you didn't mind doing a little bit of wiring, you couldn't have great success with the capacitive or inductive sensors. But again, it's all preference. It's all what you want to do with your printer, what surfaces you want to use for your printer, and that's pretty much it. So thank you all for watching. I hope you enjoyed this adventure with me. This was probably the most intense video I've ever had to put together on my channel. So thank you very much for watching. If you are part of the 78 or 79% that are watching my videos and haven't subscribed yet, if you like the content, please like and subscribe. It really helps the channel. It really helps get the word out about the channel, and it gives me incentive to do more stuff like this. So, thank you all for watching, and we'll see you soon.